How are you? Today I will discuss the topics from the chapter Electromagnetic Induction, which is chapter 4 of second sem major physics major under NEP as directed by Bankura University. Here the chapter Electromagnetic Induction, it is a famous event discovered by Michael Farad, you know, and this theory is extended after the discovery by Newman and Lenz. Here, this is the first theory of electromagnetic induction, and now I will discuss a few topics, that is self and mutual inductance and their relation. Here you know that self and mutual induction are two famous effects of electromagnetic induction. Self induction and mutual induction are two famous events under electromagnetic induction. And from self induction we get self inductance, which is denoted by capital L, and from mutual induction effect we get mutual inductance capital M. And you know the definition and unit and the significance of these two inductance, self and mutual. Today now I will discuss the relation in between self and mutual inductance. Suppose there are two coils or two current carrying conductor. Each current carrying conductor or coil having finite turns has self inductance, and for the presence of two coils there are mutual induction. Now I will discuss the relation between self inductance of two coils and their mutual inductance. Okay, now I will discuss the relation between self and mutual inductance. Here you see the figure. This is the figure of two coils. Here we use two coils C1 and C2. You see that the current flow in the coil C1 is I1 and the current flow in the coil C2 is I2. Now C1 has self inductance L1 and C2 has self inductance L2, and capital M is the mutual inductance between these two coils. Now I will discuss the relation between these self and mutual inductances. Here, if we consider that phi 11 is the magnetic flux linked in the coil C1 for the current flow in it, and phi 12 is the magnetic flux linked in coil C2 due to the current flow in coil C1. I repeat, phi 11 is the magnetic flux linked in coil C1 for the current flow in it, and phi 12 is the magnetic flux linked in coil C2 due to the current flow in coil C1. Then it is obvious that phi 12 is less than equal to phi 11. In particular case, phi 12 may be equal to phi 11, and that is called ideal coupling. But in general, phi 12 is less than phi 11. So I can write down the relation between phi 12 and phi 11 as phi 12 is equal to K1 phi 11, where K1 less than equal to 1. K1 may be 1 or fraction. Since phi 12 is less than equal to phi 11, so the relation between phi 12 and phi 11 can be written by this fashion. And here we use the constant K1 that may be 1 in ideal coupling or less than 1. So phi 12 is equal to K1 phi 11, where K1 less than equal to 1. Next. Similarly, if we consider that phi 22, here phi 22 is the magnetic flux linked in coil C2 for the current flow in it, and phi 21 is the magnetic flux linked in coil C1 for the current flow in coil C2. Then by the obvious reason, phi 21 is less than equal to phi 22. And again I repeat that for ideal coupling, phi 21 is equal to phi 22, but in general phi 21 less than phi 22. So we can relate this phi 21 and phi 22 by this fashion, similar fashion, where we use the constant K2 and K2 less than equal to 1. That is phi 21 is equal to K2 phi 22, where K2 less than equal to 1. So the previous equation phi 12 is equal to K1 phi 11, and then second equation phi21 is equal to K2 phi22. If we multiply these two equations, then we finally get phi12 phi21 is equal to K1 phi11 and K2 into K2 phi22. That is K1 K2 phi11 phi22. And I use K1 K2 is equal to K0. If we consider K0 is equal to K1 K2, then phi12 into phi21 is equal to K0 phi11 phi22. Now, what is phi12? This is related with mutual inductance. And what is phi11 phi22? They are related with self inductance. So we can write down phi12 is equal to mi1 and phi21 mi2. Similarly, phi11 L1 I1 and phi22 L2 I2. So finally we get m square is equal to K0 L1 L2 and m is equal to root over L1 L2 multiplied by K. That is m is equal to K root over L1 L2. This is the relation between mutual and self inductance. Here you see that the relation between mutual and self inductance, m is equal to K root L1 L2. M is equal to K root L1 L2. And here K is equal to root over K0, which is a coupling constant, and this is the relation between mutual and self inductance. Here you see that K less than equal to 1 because K is equal to root over K1 K2. Both K1 K2 less than equal to 1, so K less than equal to 1. Now, if K1 K2 both are equal, then K is equal to 1, and then it is called ideal coupling. And for ideal coupling, the relation is m is equal to root over L1 L2. So, particularly for ideal coupling, relation between mutual and self inductance is that m is equal to root over L1 L2, but in general m is equal to K root L1 L2, where K less than equal to 1. In particular case for ideal coupling, K is equal to 1, but in general K less than 1. Here this K is called also Naga-Oga constant. Here it is a coupling constant, but this K is called Naga-Oga constant, and it is only one for ideal coupling. And you know that in reality for transformer with soft iron core, laminated soft iron core used in transformer between primary and secondary, the coupling is ideal. So this is ideal coupling, but it is obtained in reality in case of transformer by using laminated soft iron core having very much high permeability. So here in general m is equal to K root over L2. Now student, I will discuss another topic of this electromagnetic induction next. This electromagnetic induction, I will discuss another topic, that is the reciprocity theorem. This reciprocity theorem is also known as Newman formula, because Newman and Lenz's are those masterminds who extended the theory of electromagnetic induction after discovery by Michael Faraday. Now here we have two coils. We have two coils, C1 and C2. You see the figure, and here C1 carries current I1, C2 carries current I2, and both have self inductance L1 L2 respectively, and capital M is the mutual inductance between them. But if we consider that the mutual inductance of coil C2 with respect to C1 is M12, and if we consider the mutual inductance of coil C1 with respect to C2 is M21, then eventually M12 is equal to M21 is equal to M. So we can have M is the mutual inductance between two coils. We cannot say that M12 or M21, because M12, M21 all are equal and they are equal to M. This is reciprocity theorem. So the theorem states that for presence of two coils, if M12 be the mutual inductance of one coil with respect to another coil, and M21 be the same of second coil with respect to first coil, then both are equal and they can be presented by simple M. This is reciprocity theorem, that is M12 is equal to M21 is equal to M. And here this can be obtained by a simple theoretical derivation. Here you see that if phi21 be the flux linked for mutual effect in coil C2 due to coil C1, then this is surface integration B dot NDS over the surface of the coil C2, that is enclosing the surface S2. Now here it is a fact that this phi can be presented in terms of vector potential A. Similarly, if we consider the magnetic flux linked in coil C1 due to coil C2, then this flux can also be presented in terms of magnetic vector potential, and these two presentation will give you the effect M12 is equal to M21 is equal to M. That is nothing but reciprocity theorem in mutual induction. Here I will discuss the reciprocity theorem. How can we obtain reciprocity theorem? Let us now discuss. That is M12 is equal to M21 is equal to capital M, which I have already mentioned. Here consider two coils. This is coil C1 having a voltage source, and this carries current I1, and here another coil of another voltage source carrying current I2, suppose. Okay, now this is a small current element DL1 and this is another current element DL2. The position vector of DL2 with respect to DL1 is R. Position vector of the current element DL2 with respect to DL1 is R vector. So similarly, position vector of DL1 with respect to DL2 minus R vector. Now this is coil C1, this is coil C2, and here we know that the magnetic flux linked in a surface, and that surface open surface, because magnetic flux linked in the closed surface is zero. Why? Because magnetic monopole does not exist. So you can link the magnetic flux, you can estimate magnetic flux linked in an open surface which enclose a closed boundary. So an open surface will be enclosed by a closed boundary C. So if phi be the magnetic flux linked over the open surfaces, that is phi is equal to B dot N at ds. Okay, this can be written as curl A N hat dot N at ds, where you know that A is magnetic vector potential over S, and by Stokes theorem you can represent this by phi is equal to closed path integral over C A dot dr. That is the closed contour by line integration of phi on the basis of vector potential A. So here you see that S is open surface which is enclosed by the closed line C. So this is the closed line integral. So this phi magnetic flux which is defined by this fashion can be presented in terms of vector potential. This is the actual equation which we will use in this case. Here, how can we use? Here, suppose phi 12 is the magnetic flux linked in coil C2 with respect to C1. Then phi 12 is equal to cross path integral, that is C1 over C1. Phi 12 is the magnetic flux linked in coil C2 due to coil C1. Suppose it is phi 21. Okay, phi 21. Phi 21 is the magnetic flux linked in coil C2 with respect to coil C1. Then phi 21 is equal to cross path C2 A2 dot dr2 DL2. This is magnetic flux linked in coil C2 with respect to coil C1. Magnetic flux linked in coil C2 with respect to coil C1. That is cross path integral over C2 A2 dot dr. A2 is the A2. Okay, this is A1. A1 line integration taken over C2. A1 is the magnetic vector potential given by C1 to C2. So you can write down this C2 A1 means mu 0 by 4 pi cross line over C1 dAL1 dot R outside dot dL2, because you know that A is the vector potential is equal to mu 0 by 4 pi integration over C dl vector by R. This is the mathematical expression of the vector potential for any current element or current loop. So here this is the vector potential mathematization, and we use this relation in this case. So here phi 21 is equal to mu 0 by 4 pi, here current I1 due to C1. Mu 0 by 4, this is current I. So this phi 21 we get mu 0 by 4 pi I1 cross path integral C2 cross path integral C1 dL1 dot dL2 vector divided by R. This is equation 1. This is the magnetic flux linked in coil C2 due to coil C1. Similarly, if we consider that phi 12 is the magnetic flux linked in coil C1 due to coil C2, then we get this is mu 0 by 4 pi into I2 cross path integral C1 cross path integral C2 dl2 dot dl1 vector divided by R, equation 2. So you see these two equations. By this equation, we get magnetic flux linked in coil C2 due to coil C1, and by this equation, we get magnetic flux linked in coil C1 due to C2. And both equations are obtained by the same fashion. Now, you know that phi 21 is equal to capital M21 I1. This is equation 3, suppose. And similarly, phi 12 is equal to M12 into I2. This is equation 4. Okay. Now, what I want to say that if we compare equation 1 with equation 3, we get M21 is equal to mu 0 by 4 pi cross path integral C2 cross path integral C1 dl1 dot dl2 vector divided by R. Suppose it is equation 5. And if we compare equation 2 with equation 4, we similarly get M12 is equal to mu 0 by 4 pi cross path integral C1 cross path integral C2 dl2 dot dl1 by R, equation 6. Now follow these two equations 5 and 6. Compare these two equations. Both are equal. Both are identical. So we can conclude that M12 M21 is equal to M12 is equal to M. So we need not mention M12 and M21. We should mention only M for mutual inductance between two coils. And this is reciprocity theorem, where we get M12 is equal to M21 is equal to M. This is reciprocity theorem. So you see that we use the basic definition of magnetic flux in terms of magnetic induction, and we convert it in terms of magnetic vector potential. And by using the basic formulation of vector potential, we get phi 21 and similarly phi 12. Phi 21 flux linked in C2 due to C1, phi 12 flux linked in C1 due to C2. And both are compared with two basic equation 3 and 4, and finally we get M12 and M21, and finally we get both are equal. Both are equal, and this is mutual inductance, and we should mention M, not M12, not M21, M, because both are equal, and this is reciprocity theorem, and this is derived by Newman, and this is also known as Newman formula. Not only that, this is established, but here we also get the expression of flux linked in one coil with respect to another coil in terms of vector potential, in terms of current element. Okay, thank you.